In the last video, we looked at the general conjunction rule, which involves the use of conditional probabilities. Now, if you look at this expression for conditional probability on the screen, which I'm calling the general conditional probability rule, you might notice that it's exactly the same formula as the general conjunction rule. It's just rearranged. This is in fact how conditional probability is defined in standard probability theory. In this video, I want to explore what this formula means from the sample space perspective, with the hope that it'll help to develop some intuitions about why it works. Let me say up front that I'm not going to be talking about the Bayes rule formulation of conditional probability here. I'm going to save that for another video. Let's start off with a simple example to refresh our memories. Consider these two events. The first event is rolling a 2 on a dice roll. We'll label this event with the number 2. The second event is rolling an even number on a dice roll. We'll label this event E. Now we'll call a probability a categorical probability if we're just talking about the probability of an event that is not conditional on other events. So we're just asking about the probability of A occurring. We're not asking about the probability of A given some other event occurs. We contrast categorical probabilities with conditional probabilities. Here we're asking about the probability of A given that some other event B has occurred. Or in other words, we're asking about the probability of A on the condition that B occurs. So with these two events, what are the categorical probabilities? That's easy. The probability of rolling a 2 is 1 in 6, and the probability of rolling an even number is 3 in 6, or 1/2. But of course, we're interested in conditional probabilities. So a natural question to ask is, what is the probability of rolling a 2 given that it's even? And we know the answer to this just by inspection. If the dice roll is either a 2, a 4, or a 6, then the probability that it's a 2 is just 1/3. Now let's see how this answer squares with our definition of conditional probability. Here's our definition in terms of general events A and B. The probability of A given B is equal to the probability of the conjunction of A and B divided by the unconditional probability of B all by itself. And if we substitute our events for this example, it looks like this. The probability of rolling a 2, given that it's even, equals the probability of rolling both a 2 and an even number divided by the probability of just rolling an even number. Now we know the value of the denominator term, it's just 1/2. The numerator is the only tricky part. It's a conjunction, and in the last video we covered the general conjunction rule. In fact, this is just another way of writing the general conjunction rule. The question we want to ask is this: how many possible dice rolls are there when the dice roll is both a 2 and even? Answer: just one. Rolling a 2 is the only dice roll that is both a 2 and even, and the probability of rolling a 2 is just 1 in 6, right? So now we have our numbers. The probability of rolling 2 and even is 1 in 6, since there's only one dice roll that satisfies this condition. The probability of even is 1/2. 1/6 divided by 1/2 is the same as 2 divided by 6, or 1/3. And this is indeed the answer that we figured out just by inspection. So the formula works. Now, I know for a fact that a lot of students don't have a good intuitive sense of why it works. They're not exactly sure why the conjunction is relevant, and they're not sure why we're dividing by the probability of the conditioning event. To help see why the formula makes sense, it helps to look at the situation from the sample space perspective. Here's our generic sample space that we're familiar with from previous videos. The blue square, labeled omega, represents the set of all possible outcomes of a probabilistic trial, or what we've been calling the sample space. Events are represented by subsets of this sample space, and probabilities of events are represented by the area of the subset associated with a given event. So in this example, the ovals labeled A and B are events, and the areas of A and B are proportional to the probability of A and B occurring. If we consider the area of the whole sample space, omega, then we assign this probability 1, which means that the outcome has to land somewhere inside this area. If we think of a probabilistic trial by analogy with randomly throwing a dart at a board, then we're saying that the dart is guaranteed to land somewhere inside the blue square. Now, in this diagram, A and B overlap. This represents events where A and B both occur at the same time, indicating that they aren't mutually exclusive events. In previous videos, we used the example of drawing a playing card that is both a face card and a spade. In this video, we use the example of getting a dice roll that is both an even number and a 2. The area of this overlap region represents the probability that both A and B will occur. Okay, let's clear the darts off the board. And now let's ask the question, how is conditional probability represented on this diagram? Well, here's our formula for the probability of A given B. And let's think about what's going on when we ask, what is the probability of A given B? What we're saying is that, in this case, we know some additional information that we didn't know before. We know that event B occurred. This is like saying that we know that our dart landed somewhere inside B. So we're saying, given that we know the dart landed in B, what are the odds that it also landed in A? In other words, given that we know the dart landed inside B, what are the odds that the dart landed in the overlap region between A and B? The overlap region makes up a fraction of B, and that is precisely the fraction that we're trying to estimate with the conditional probability rule. We're asking for the ratio of the overlap region to the area of B. We can say the same thing with a slightly different emphasis. When we know that B is true, or that B occurred, what we're saying is that we're no longer dealing with the whole sample space. We're dealing with a reduced sample space, and treating this as our new omega. The conditional probability of A given B is the area of the overlap region, the events where A and B both occur, divided not by the area of the original sample space, but by the area of the reduced sample space, B. I like the darts, so let's put them back on. Now I think it's much easier to visualize what the numerator and the denominator represent in the general rule for conditional probability. Also, notice that this discussion is consistent with what we did when we solved the dice problem. Here's our original sample space for a dice roll. Omega is equal to the set of equally probable outcomes 1 through 6. We imagine assigning an area to this set equal to 1. The event of rolling a 2 is a subset of this sample space. In this case, the 2 takes up exactly 1/6 of the total area, so the probability is 1/6. The event of rolling an even number is a different, larger subset. It takes up exactly 1/2 of the total area, so the probability is 1/2. Now, if we're considering the probability of rolling a 2 given that it's even, we're dealing with a reduced sample space. We're treating the evens as the new sample space, and looking at the proportion of events corresponding to the number 2 as a fraction of this new sample space. And we get the answer 1/3. And note that the 2's are entirely within the evens. This corresponds to a sample space that looks like this. Here the overlap is complete, with the 2 a proper subset of the evens. But the formula works all the same. If A is included inside B, then the intersection of A and B is just equal to the area of A. In this case, the intersection of 2 and E is just equal to the area of 2. This simplifies the calculation. The numerator is just the area of 2, and the denominator is just the area of E. When we plug in the probabilities, we get our answer, 1/3. Now, for the sake of completeness, let's work it the other way. What's the probability of the dice landing even, given that it's at 2? Well, we know the answer to this already. It's got to be equal to 1, since 2 is an even number. The calculation gets it right too. We use the fact, once again, that the area of overlap is just equal to the area of 2, so the probability of E and 2 is just equal to the probability of 2. And now the conditional probability is just 1/2 over 1/2, which is equal to 1. And that's the answer that we want. It's like asking what's the probability that the dart landed on the 2, given that it landed on the 2. That's a sure bet. Okay, that wraps up this introduction to the general conditional probability rule in probability theory. I hope this video gives you a better sense of why the rule has the form it does and why it works. In the next video in this series, we're going to be looking at a special form of the conditional probability rule known as Bayes' rule.